Коля, вы в Швейцарию не поступали? Забыл. И как? Там все работает, да? Спасибо.
Саша с Англией пришли в опера, а пока не пришел.
Почему?
Ну, у меня все остальные письма приходили в офер, и в какой-то момент мой паспорт не понравился, потому что у меня сохранения тогда еще не было. Я ему достал, но это было относительно недавно. Поэтому я надеюсь, что просто позже пришлют.
Да. So let's start. And the last time we introduced the notion of Fabinho splitting and derived certain corollaries from its existence, like higher cohomology vanishing. Today we'll discuss some criteria for the existence of Fabinho splitting. The Fabinho splitting was a morphism from the push forward perspective Fabinho's of the structure sheaf to itself that splitted the canonical map like this. So we are interested in the existence of such splitting. Fine. So we'll study the homomorphisms from this to that, and inside this space of homomorphisms, we're interested in such phi's that phi of 1 is 1, that's surjective. So we want the evaluation morphism epsilon from, say, the local home sheaf from the push forward of O to itself to the structure sheaf, namely phi goes to phi of 1. We want this to be surjective. So, in a sense, this is our basic criterion, but it is too simple-minded. We want to translate it further on in order to obtain something useful. Okay, and let me apply some general nonsense with adjoint functors and such, and we will obtain some sort of criterion, and then we will study it in examples and in depth, and arrive at something computable and useful. Okay, but I will start with something clever, but don't be intimidated. So later on we will respell it in some down-to-earth terms. Okay. Yes. I mean that it's really splitting, that the composition is 1. Yeah, that's what you mean, I hope. Yeah. Well,
why from subjectivity follows that there is a homomorphism with such properties?
Yeah, we'll see. So just let me formulate something to start with. Okay, so first of all, I claim that there is a functor upper shriek. So this is a right adjoint to the push forward like this. So the left adjoint is the Fabinho's upper star, the usual pullback. It's left adjoint. But there is also a right adjoint like this. And then this local home is just equal to the push forward of this shriek pullback of OX, just by definition. Also, there is some Serre duality for the finite morphism. Fabinho's says that the shriek pullback of the structure sheaf is the internal home from the star pullback of the canonical the dualizing sheaf into itself. Okay, and well, at least this is true if X is smooth, and hence Fabinho's is flat, and also the dualizing sheaf is a line bundle. Okay. In fact, in all our applications, X will be smooth, like flag variety. So this is not a problem. And now we will. Well, let me just say that there is the trace morphism. And later on today, we will construct, for example, this trace morphism explicitly, and everything I'm formulating now will be done explicitly. Just I am formulating it in a fancy way. Tau from the push forward of the dualizing sheaf to dualizing sheaf. And in fact, something like this we did for curves. If, well, in the exercises for curves, you constructed like trace map from push forward for any morphism between curves, for any finite morphism between curves, like this. And now this is a finite morphism in arbitrary dimension, but purely inseparable. Okay. So we'll have such a trace morphism such that the evaluation epsilon, this evaluation, as a map from Fabinho's. So I'm using this. I'm using that the internal home we're interested in is such a push forward. Okay. It is the same as the internal home from the canonical dualizing sheaf to its push forward just by adjunction. And now we'll go to OX. So this is identified with composition. Yes. I want to translate this surjectivity to some other statement, which we will eventually check sometimes. This maps to endomorphisms of omega x, and this is just, since omega x is a line bundle, this is just the structure sheaf, and this map is U goes to a composition of the trace with U. Okay, so this evaluation is the same as just composition with trace. That's what I claim.
Why your epsilon goes from this U?
Yeah.
It goes from internal form, which you identify with push forward.
Yes.
Push forward, Fabinho's and upper.
Mm-hmm.
Push forward.
Yeah. But you ask why I write this? That's the question. Without this, probably you don't have. Yes, from that. So I rewrite this in this way, then I compute the Schritt pullback like this, and that's what I obtain.
How do we use certiorari?
Pardon me?
How do
Yes.
we use certiorari? It's something about homology.
Yes. So why this is called Serre duality or what? Maybe let me skip this now. I think we discussed this over Zoom like a couple of months ago in the end of some lecture, but maybe let me not repeat it now. This one? This one just the composition with the trace. We have homomorphism here, and then from here to back to omega x. So we get endomorphism omega x. This is just O. Okay. So now last time we computed the push forward, pull back of any line bundle, in particular the dualizing canonical line bundle, and this is just the tensor pth power. Okay. So it's another line bundle, and now we have homomorphism from one line bundle to another line bundle, and so it means that the Schritt pullback of OX is homomorphism from this to omega x itself. So it's just omega x to the tensor power 1 minus p. Okay. Fine. And somehow we will use we'll formulate some criterion in terms of this power of the dualizing sheaf. And now let's consider an example. Last time we had also some example for affine space, and we'll just reconsider this affine space example. So X will be the affine space and dimensional, and the functions, global sections of OX sorry, will just polynomial ring. And now it acts on the homomorphisms from Fabinho's push forward to OX. And this is the same as global sections of the affine space with coefficients in the push forward of this Schrieg pullback of OX. Okay, and what is this? This is the set of endomorphins from the polynomial ring to itself. Well, these are global sections of the internal home, so just the usual home. But for a fine space, there's no difference between sheaves and their global sections, yeah, by localization, so I don't have to distinguish. Okay, so we get the space of endomorphisms such that of phi of f to the p g equals f phi of g. And it's a model over the functions, so it has an action f phi applied to g is f phi applied to g. Okay, but we also have one more action. Say f star phi applied to g is phi applied to fg. Okay. And then the two actions are related in an obvious manner. So if I act by f to the power p on g, on phi, this is the same as I just act like this. Okay. So now we set the trace map from the polynomial ring to itself. An additive map. Defined as follows. So on monomials. So it somehow extracts, so to say, pth root. And in what sense does it extract pth root? So this is so if I is p minus 1 plus pj and 0 otherwise. Okay, so for example, if you have monomial t1 to the power p minus 1 times t2 to the power p minus 1 times so on times tn to the p minus 1, then this goes to just the product of. Oh, sorry. This just goes to 1. Sorry. Just goes to 1. By definition. Okay, and that's related to this fact. You see. Okay. Well, let's prove the following claim that the global sections of the Fabinho's pullback of the structure sheaf is a free module over the polynomial ring with respect to the star action with generator of this trace. Okay, so that's the importance of this trace. It just generates the whole module of sections.
Could you comment on this computation? Why it is a homomorphism? Yes.
So far there was no computation. I just announced that I consider such a thing, but it is an important thing since it generates the whole module. It's the generator of this module of phi's.
The trace is from home from Fabinho's pullback of dualizing shift to dualizing shift.
It will be also identified with this, but so far we just consider the sections of this, or else the homomorphism from this to that.
I mean, the trace we
Yes.
define as map on polynomial ring.
Yes. Mm-hmm.
And this is
But you see, it's hard to in this simplest example, because we have a flat space, it's hard to distinguish between various substances because the dualizing shift is also trivial. So, in fact, all the models in questions are just rank 1 free modules. Okay, but just the interesting thing maybe is to find their generator. In particular, here the generator will be given by that. So that's what we have to check.
That phi should
Yes.
be k-linear or
Well, that's what we have. This is the condition. Sort of Fabinho's linear, yeah.
yes, it's not linear.
In particular, yeah. So if you apply Fabinho's on K itself, it will be. So in particular, if F is a constant, then you will have. So it's so-called Fabinho's linear. Semi-linear, I don't know.
and they additive.
Yes, absolutely. Okay. Let's check this. Well, let's take some element phi in the global sections. And this is, as we know, the same as home from Fabinho's push forward to the structure sheaf. And now we set some polynomial function f, the sum over all monomials of. Okay, so I is small, so p minus 1 minus I is also positive. Okay, so this is some polynomial. There are finitely many summands. And then we have that our phi is the star action of this polynomial f on trace. And hence, the trace is a generator. The star action is here. Generator. And now we have to check that there are no relations. That's a free rank 1 module. So if there is some function that annihilates, then we can iterate this, and we say that see that f to the power p action on trace is also 0, but on the other hand, this is equal to f times trace. But certainly there are no zero divisors in polynomial ring, so this means that f is 0, right? Because there are no zero divisors. Okay, so the claim is proved. So this is the importance of such a trace, and now, well, I raised already the evaluation, but let me recall it. The evaluation epsilon, that was from functions, sections with coefficients and the Fabinho's pullback of OX, to the global sections of OX, so just functions, polynomial ring. Yes. Yes. You're asking about this, or about what? Here? Here? This is just the relation between two actions here. Okay, so our evaluation is the composition. Applied to 1. So this is just a trace of f. And it means that the composition f, the action of f on a trace is a Fabinho splitting. If we have two conditions, first of all, the product of p minus first powers enters f with coefficient 1, and second, f does not contain monomials t to the power p minus plus something divisible by p for positive j. Well, because it corresponds to this tau morphism from the push forward of
This is actual trend, it's extension of fields.
Well, in a sense, yes, but well.
Of vector space.
Well. So you ask about etymology. Why is it called trace, or what's the question?
Yes, I mean, this is actual trace only for curves, and for other manifolds, it just called that way because it is trace for curves.
Well, maybe so. For curves, it was discussed in the home assignments about residues, and yes, it is. As I remember, it's related to trace, and well, in fact, in general, it is also has some categorical trace meaning, but maybe let's not discuss this now. Okay, so so that's it, and we classify all the possible Fabinho splittings for the affine space. That's the result. Okay, and so last time we had example 1, and this Fabinho splitting of this first example corresponds to the simplest solution when f is just t to the power p minus 1. Okay. Okay. So now we have to we want to in a sense globalize this example. Go to arbitrary smooth variety, and also to construct this upper shriek and the trace map and everything we used so far. So let's. Yes. All the Fabinho splittings on the affine space, I classified all.
For each Fabinho splitting corresponds to something.
Yes.
To what?
To the morphism from Fabinho's push forward of the structure sheaf to the structure sheaf itself, and then we classified all the possible such morphisms, and among them we specify the splittings. The splittings are given by such polynomials.
There's a bijection of two sets.
Yes.
Morphisms.
So we have the Fabinho's from OX to Fabinho's OX, and we want the splitting back here. Okay, so at least this phi lives in all the possible homomorphisms from like this. Okay, and now I computed all the possible homomorphisms. It was the free rank 1 module with this generator. Okay, and then among all its elements, I specify those which are actually are splittings. Good. Okay, so this globalization will take up all the remaining time, and it will be, in fact, the so-called Cartier Operations. And I will now explain what is this. And this is something also very specific to fine characteristic. We always have the RAM complex. OX goes to 1 forms, then goes to degree 2 forms, and so on. And then you go to the dimension of X, and then it stops. Okay, well, it has some cohomology, and if you just take global sections and say over real numbers, and when I consider smooth forms, infinitely differentiable forms, then those sheaves are soft. I think they're called soft, so they have no higher cohomology, each one of them. But in fact, this whole thing is a resolution of the constant sheaf, like this. And so just taking global sections of the RAM complex computes the cohomology of the constant sheaf. That is the singular usual cohomology of our variety in characteristic 0, say over real numbers in C infinity setting. But in characteristic P, something absolutely new happens, and unexpected probably. That the RAM complex stops being a resolution. It has local cohomology. And so now over characteristic P field, the RAM complex is not exact anymore.
It's when X is smooth?
Yes. Mm-hmm. So for a smooth X. Oh yes, certainly. Yes, that's what we'll do right now. I'm just giving an announcement of what will happen in 5 minutes. So it will be not exact, and it's local cohomology is in fact isomorphic to the complex itself. Well, maybe Fabinho is twisted by, but but just like this.
It's because d of p's power is 0.
Yes, absolutely, yes. And this isomorphism is called Cartier Operations. So that's what we will construct now. And then we will see that this trace tau is nothing but the topmost Cartier operation. Local cohomology. I mean, cohomology is a complex of sheaves. So it's boundaries modular, or cycles modular, cocycles modular coboundaries. No, not hypercohomology, local cohomology, sheaves. Yes. Not global cohomology, local, the sheaves. Global cohomology are vector spaces, and I'm talking about sheaves, coherent sheaves. What? Why this is true? I will explain this right away. So tau is the top Cartier operation. Okay. So, well, we will first go back to the local situation, but not flat affine space, but the affine variety. And then we have the Kähler differentials. And we have the differential, the universal differential, A from omega 1. So we did discuss this a few months ago, and now in the characteristic P we have that d a to the power P is 0, and hence d is linear over a to the power P. Okay, it's also a subring, subalgebra. Okay, now the Ram complex, which we didn't use so far. We set omega d a is the exterior dth power of omega 1. So it's an a module. Maybe let me say that the whole thing, the whole exterior algebra, so it's a module with generators, just differentials dA, and relations of the exterior algebra, and also the Leibniz rule, a dB plus b dA, and also d. If I take two exterior forms like alpha and beta and capital differential, it will be d alpha wedge beta plus minus 1 to the degree of alpha, alpha wedge d beta. And now what is d? It's the Ram differential. So it extends from we only had differential from a to the first power, but then using these relations, we can extend it to arbitrary powers. So d extends and d square is 0, and also d is a to the power p linear, as it was on the very first component. Okay, now we can consider the cohomology. H of this drum complex. Okay, and everything here is finitely generated. Over a to, so since the differential is linear over pth powers in A, then its cohomology is a model over pth power subring, and it's finally generated over e to the p. Okay, so now this will be the crucial definition for Cartier operations, although it's inverse to Cartier operations, but we start with gamma from A to the first Kähler differentials, namely it takes A to the power p minus 1 times d. Okay, and now let's prove a lemma. First of all, that gamma of AB is a to the power p gamma of b plus b to the power p gamma of A. Also, gamma is exact. And finally, gamma is additive. Modulo coboundaries. So model differentials. Okay, and A and B parts are evident. We only have to check the third part, C, and then we use the Newton binomial formula. So we compute d of a plus b to the power p is p times a plus b to the power p minus 1 times d of a plus b, and this is p times a to the p minus 1 dA plus b to the p minus 1 dB, plus something which vanishes. So it's the sum from I equals 1 to p minus 1. P choose I, d a to the I, b to the p minus I. Well, anyway, this has some integral coefficients, and we know that p choose I is divisible by p in this sum. So there are extremal terms like this, and the internal terms like that, and the internal terms are divisible by p, and so it implies that a plus b to the p minus 1 d a plus b minus a to the p minus 1 dA minus b p minus 1 dB is differential of some polynomial q of ab where some integral some polynomial with integral coefficients. Okay. So we proved our lemma. And it implies that the composition to yeah, so by part B, it goes to cocycles. Okay, and then we can project to cohomology. Yes. So if I have map from A to the first differentials, now it goes into cocycles. The cocycles project onto quotient modular coboundaries, so the first cohomology, and this is a derivation. Let's also call it gamma. With respect to so it's a morphism from A to first cohomology. So when I say that it's a derivation, I must explain what is the model structure. Yes. So the model structure is that A acts on itself just by multiplication. And A acts on the first cohomology by multiplication by Fabinho's of A, that is A to the power P. Okay. Okay. So from the universal property of Kähler differentials, we get a morphism from Kähler differentials to the first cohomology Yeah, because any derivation factors through the Keller forms, so we get a linear yes, gamma is a derivation, yes. So this composition, also called gamma, is a derivation, and so we get an a linear map gamma from the first differentials to the first cohomology with the property that a dB goes to a to the power p, b to the power p minus 1 dB. Well, modular coboundaries. Okay. And furthermore, since the gamma of dA wedge gamma of dA is 0, we can extend to the homomorphism of the whole de Rham algebras gamma from the Keller differentials to the cohomology algebra. And again, it's a linear. Say A1 d A2 wedge d AI goes to A1 to the power p minus 1. Sorry, A1 to the power p, A2 to the power p minus 1, dA2, and so on, and then AI to the power p minus 1, dAI. And again, modulo coboundaries. No. Well, this is the de Rham complex. But we somehow disregard this differential here. It is equipped with the de Rham differential, but it doesn't matter to us at the moment. This is just a graded algebra without any differential at all. Yes.
Gamma is algebra homomorphism.
No, as you see, no. It's only a linear, but not a linear algebra, but not an algebra homomorphism. Though these two are both supercommutative algebras. Well, this is sort of say DG algebra equal to the differential. This is without any differential, okay? But we have such a homomorphism defined by this formula.
How to get homomorphism from Keller differential to H1?
How did we get this? Well, just here I explained. Because we have this gamma, and this gamma is derivation, but any derivation by the universal property of Keller differentials gives rise to a homomorphism from Keller differentials to the target. Yeah, any differential from A to AM, any derivation gives rise to such a thing.
And then you extend it.
It's well, somehow geometrically in the standard differential geometry, it's expression of the fact that these sections of cotangent bundle and they are dual to sections of tangent bundle. The sections of tangent bundle are vector fields, but vector fields act as derivations of the functions ring. And this is just an algebraic reformulation of this result.
From the universal property, okay.
Yes, just from the universal property, as it is written here. Okay. Okay. Only maybe I have to add once again that when I say A linear, then I mean that the action of A on the cohomology is via Fabinho's, via pth powers. Is via a to the power p. So here the action is just usual action, and here via pth powers, as we had here. Fine. So now the basic theorem is that if A is regular, that means that the spectrum of A is smooth. Then gamma is an isomorphism. Okay. So that's what I announced. And then, well, it's defined locally, but certainly it glues and globalizes. So if we have any smooth variety, we will have an isomorphism of the RAM complex and its local cohomology
They are the
sheaves.
same as A modules.
Yes, as A modules, but with respect to the Fabinho's twisted action on the right-hand side.
And globally, they would be the same as sheaves.
Yes, sheaves, yes, but this sheaf will be via Fabinho's action of the structure sheaf.
So there would be action of Fabinho's pullback.
Yes, yes. Okay, so let's try to prove it. Well, it suffices to check after localization. Oops, sorry. And completion. Pardon me? Completion? Just again, it suffices to check at the fibers, and the fibers do not change under these operations. So okay, but after this completion, we just get a power series ring. And then we can just write down explicit formulas, and that's what we'll do. Okay, so we'll do this by induction in N, in the number of variables in the dimension of our ring. Well, okay, if you want. So we start with arbitrary regular ring, meaning that its spectrum is smooth. And and then we check at any maximal ideal. So we localize at any maximal ideal and complete this maximal ideal and obtain the Laurent formal series ring. Sorry, Taylor formal series ring. Yeah, and let's compute there. So first, let's prove surjectivity. So we have alpha and I form, which is exact, and we wanna represent it as gamma of something modulo coboundaries. So let's write it in the following form: as a series in Tn. Tn to the power j, and then we'll have alpha j plus beta j times dTn. So here alpha j will be an I form in one less variable, so without Tn. And beta j is degree I-1 form in the other variables. Okay, so we will reduce to some computation in this smaller power series ring where we know the result by induction assumption. Yeah. So I just decomposed my form as a, yeah, nothing clever. So we know that alpha is closed, and it implies that all those coefficients alpha j are also closed, and also that minus 1 to the power I sorry, to the power j alpha j plus 1 plus d beta j is 0 for any j. Okay, and then it implies that Tn to the power j plus 1 times alpha j plus 1 plus Tn to the power j beta j times dTn is minus 1 to the power j minus 1 over j plus 1 dt and g plus 1 beta j. If j plus 1 is not divisible by p, otherwise the denominator vanishes and we cannot write this equality, solve this equation. Okay, so it implies that alpha is the sum of Tn to the power p times j alpha pj plus Tn to the power pj minus 1 beta pj minus 1 times dTn modulo differentials, the closed forms. Yeah, and so in fact, I'm sorry, in the powers here it's y. Y is our degree of our form. Yeah. Okay. And here it's possible to have j equals 0, so beta minus 1 is 0. Okay. And what we have that the differential of alpha pj is 0 for any j, and it means that the image of Tn to the power pj alpha pj in the cohomology lies in the image of gamma by our induction assumption. Okay, and similarly with the image of Tn to the power pj minus 1 beta pj minus 1 times wedge dtn. Okay, again in the ith cohomology. Okay, and this is true since we know that pj minus 1 lies in omega I minus 1 over n minus 1 variables, and the differential of beta pj minus 1 is 0 because of this. Okay. So we conclude that gamma is surjective. Okay. Now I have to prove injectivity. So assume that there is a form alpha such that gamma kills alpha. Well, write it down in the same form as we did, and then gamma of alpha is the sum from j equals 0 to infinity to Tn to the power pj gamma of alpha j plus Tn to the power p minus 1 gamma of beta j wedge dtn modulo coboundaries. Okay, and this is again modulo coboundaries equal to the sum over all j Tn to the power pj, alpha j to the power p plus Tn to the power p minus 1. Oh, sorry, it's some other alpha, it's some other beta, I'm sorry. And so here, this other alpha j is gamma of alpha j, and other beta is gamma of beta j. Okay, so these are cocycles. But in one less variable. So we know the gamma of alpha is 0, and hence this infinite sum Tn to the power pj alpha j prime plus Tn p minus 1 beta j prime wedge dtn. This whole thing is a coboundary. And then it follows by the same argument as here that alpha prime j is a coboundary. And beta prime j also is a coboundary, and then by the induction assumption they're both 0, and hence alpha j is 0 and beta j is 0, and we are done. Okay, yes?
Why alpha prime and beta prime are coboundaries?
Just because
This is
but-
all coboundary.
so the whole thing is a coboundary, and just I think as we argued here, so we had
Can we get it just from
yeah.
we can represent some form from degree minus 1 in the same manner?
Yes.
We can memorize.
Mm.
Can it be done explicitly?
Mm. mm, yeah, I think because the differential of this is 0, but by the Leibniz rule, yeah, just if you know that t to the power p alpha prime is d d omega, then mm, 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 let's see.
I think it's
Mm.
clear why alpha is co-bounded.
Yes. So, well, I want to write that alpha prime is something like this, yeah? It must be divisible. Well, maybe I should write omega t minus p, yeah? Mm,
Because alpha prime is, it's clear that it's co-bounded.
yes. And then was the question?
Why isn't it?
Why beta? Uh, mm, mhm.
Maybe for the same reason.
Uh, but here I used the linearity with respect to pth powers. Yeah, and for beta we'll have p minus first power.
Beta can appear from differentiation t because we need to differentiate t.
Yes.
P's power and it would be 0. So it
Uh,
appears only from the co-boundary in other variables.
okay. So say it again.
I mean, we can't obtain such a term by differentiating t because
Which t? Tn, yes.
because we get 0.
Right.
So it's only obtained by
The differentiating
yes,
something
by
else.
product
Mhm,
with
mhm.
some co-boundary. So
Okay. 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 Thank you. So next time we'll start by defining Cartier operations that will be inverse to this, and then apply to. So I hope next time we'll formulate the criteria for Fabinho splitting, and then start applying them to flag varieties and things like this.
Скажите, пожалуйста, возможно как-то курсивом написать следующую дату?